On July 30th, 2020, whilst the world was in the grip of a coronavirus pandemic, the Perseverance Rover launched on an Atlas V541 rocket from Cape Canaveral Air Force Station in Florida. Almost 7 months later, on February 18th, 2021, the world watched on anxiously as Perseverance successfully landed on Jezero Crater, Mars. The mission represents the first dedicated and directed search of signs of life on Mars since the Viking landers in 1976, and it is the first rover to attempt this. All the other Mars rover surface missions, including Spirit, Opportunity and Curiosity, were primarily designed to look for ancient signs of past open water on the Martian surface. They had some ability to perform geochemical analysis, and certainly their camera capabilities could have detected obvious physical signs of past or present life. However, proof of life was not their primary purpose, and despite some claims on internet forums, officially they didn't detect any obvious signs. However, there are scientists who think that the Viking landers did in fact detect signs of current life, although other scientists have been cautious about this, and have offered alternative explanations for the results of the Viking experiments. So now is the time to resolve this uncertainty. Perseverance is different, and its search for signs of life will be in 2 stages, one immediate and the other some years away. Let's take a look at these stages. This location was chosen because approximately 3.5 billion years ago, the crater was a lake that was fed by a river that coursed through the rim, creating a delta where sediment from elsewhere collected and settled. The lakebed itself around the edge of the crater appears to be permeated with calcium carbonate, which we know on Earth provides a suitable environment for the preservation of small organisms, including microbes. Sediments may have been transported considerable distances before settling in Jezero, and so the delta will provide a broad sampling of deposits swept up along the river's course, as well as signs within the crater lake itself. Perseverance carries an array of different types of cameras with different capabilities. There is Mastcam-Z on Perseverance's mast, which is able to perform a close-up visual inspection of anything that may look interesting. Mastcam-Z consists of 2 zoom cameras that can see 3D images in the red, green, blue spectrum, and also at the visible and near-infrared wavelengths. SuperCam consists of a camera, 2 lasers, and 4 spectrometers. According to NASA, SuperCam can identify the geochemical makeup of a target as small as a pencil point from a distance of 20 feet. Its lasers can vaporize interesting sediments into a tiny puff of plasma, which can be spectroscopically analyzed for any interesting components. If Mastcam-Z and SuperCam come across interesting things, Perseverance will further investigate using Pixel, planetary instrument for X-ray lithochemistry, and Sherlock, scanning habitable environments with Raman and luminescence for organics and chemicals. Pixel contains an ultra-small X-ray spectrometer and a camera, and can detect over 20 chemical markers of possible life in a sample as small as a grain of table salt. Pixel has a mobile component, sometimes described as a large insect, that will operate during Martian nights and when temperatures are more stable, and will move at 100 micron intervals to zoom in on potential targets. Sherlock uses a type of spectroscopy called Raman spectroscopy, which typically detects vibrational modes of individual species and molecules. This data will be superimposed on images taken by its camera, called Watson, to identify specific distributions of interesting chemistry, determining sampling locations for the 2nd stage sample return mission. The main reason why NASA and ESA scientists spent time training in Pilbara in the Australian outback is that Pilbara is a site of some of the oldest signs of life on Earth, at least 3.5 billion years old. Among the fossils at Pilbara are accumulations of microbial mats that have been built up over billions of years to create what are called stromatolites. These are mounds of microbial cells interspersed with layers of calcium carbonate that can be quite large with a wavy layered structure. To the trained eye, they can be quite distinctive. Something like stromatolites may very well have been formed in the presence of microorganisms in the Jezero Crater lake basin around the calcium carbonate rim deposits and in the river delta formation. This is why Mastcam-Z, SuperCam, PIXL and Sherlock are so heavily loaded with various types of cameras and instruments for geochemical analysis. However, the scientists on Earth will still need to be able to recognise potentially interesting features and plan what instructions to send to the rovers to direct them to interesting and potentially promising formations. Of course, we have no way of knowing if there are stromatolites on Mars, but they seem like a very likely candidate for early and relatively easy recognised signs of microbial activity, and Jezero Crater is a prime candidate to have these kinds of things. Martian stromatolites do not have to look exactly like terrestrial stromatolites, and may not even have identifiable structure since, on Earth, there are things called thrombolites, which are also collections of bacterial colonies, except that unlike stromatolites, they look like clumped tangles of sediment. But seeing this on Mars is also likely to be interesting and worth investigating. There may also have been simple organisms with shells on Mars, just as there have been on Earth, and these may also, in principle, be recognisable using the capabilities of the instruments on Perseverance. It seems extremely unlikely that we will see anything like snail shells or the chambered shells of various cephalopods, because we don't think that Mars was habitable long enough for such complex organisms to evolve. But we really won't know until we start looking. This will be an extraordinarily complex part of the mission and will involve close cooperation with the ESA. The instrumentation required to definitively test for past or present life on Mars is just too complex, large, and heavy to carry on a rover, and so they somehow need to have samples back here on Earth, to study in modern laboratories. Even a human-crewed mission to Mars, still decades in the future, wouldn't be able to carry this kind of instrumentation and would still have to return samples to Earth, so they are going to do this robotically with the Mars sample return missions. Perseverance carries about 43 little titanium tubes with it, each less than 6 inches, or 15.2 centimeters long and hypersterilised, which will be used to store sediment core samples that it will drill and retrieve from any interesting sites its instrumentation has identified. These will be triple sealed and cached in predetermined places for later retrieval. The sampling, recovery and storage portion of the Perseverance mission is only supposed to last about 2 Earth years, although if the past is any indication of the future, Perseverance, with its plutonium power source, may last for many more years than that, and will continue to return data about Mars. In 2026, the Sample Lander and Rover Retrieval mission designed by the ESA will launch from the US and land on Mars. The rover will collect the samples and return them to the lander, which will have a small rocket and launch system on it to blast them into Mars's orbit. Because only some of the samples will fit into the orbiting sample canister, the rest will stay on Mars for future missions. The orbiting sample canister will achieve Mars's orbit for 5 years until the ESA launches in 2031 with the Earth Return Orbiter, which will capture the orbiting canister and return it to Earth, and that is when the in-depth scientific analysis will begin. In the meantime, the ESA ExoMars, with the Rosalind Franklin lander, will have arrived at Mars by 2022, doing its own scientific investigations, and we will be getting results from that as well. The mission is nothing less than astonishing. The engineering and AI capabilities are difficult to fathom. The world stood still as they watched live the successful landing of Perseverance, but that was just the beginning of possibly 10 years of work that will hopefully prove once and for all if there is, or once was, life on Mars. And if the stunning photographs that have emerged since Perseverance landed are anything to go by, it's going to be an exciting journey.